So what is the problem with the way we define acidic, basic, and neutral solutions? Well, the problem is that the numbers are a bit cumbersome. So because we are working with powers of 10 and negative powers of 10. So we are thinking about 10 to the minus 8, 10 to the minus 6, 10 to the minus 7. It's not easy to compare. If I compare 10 to the minus 6 and 10 to the minus 7 and I tell you which one is larger, well, 10 to the minus 7 is 10 to the minus 7 is smaller than 10 to the minus 6. 10 to the minus 8 is smaller than 10 to the minus 7. And that I can do that in my mind, but it's not something as easy as comparing 1, 2, 3, or 10 with 8. If I compare 10 to the minus 6 and 10 to the minus 7, I have to think for a second which number is larger. If I compare 6 and 7, I can easily know which one is larger. So enter Danish chemist Sorensen, who lived in between the 19th and 20th century, that came up with a pH scale. He said, let's not look at the concentration of hydrogen ions. Let's look at minus log in base 10 of the concentration of hydrogen ions. Why? Because it doesn't sound like, oh, adding logs doesn't sound like, a minus log doesn't sound like particular improvement. Because if you do minus log of 10 to the minus 6, that's 6. Minus log of 10 to the minus 8 is 8. Minus log of 10 to the minus 7 is 7. So suddenly you're not comparing minus 10 to the minus 7, 10 to the minus 8, 10 to the minus 6. You are comparing 7, 6, 7, and 8. And comparisons become easier. So what happens with the pH scale, and what's an acidic, a basic, and a neutral solution if you use pH instead of concentration of hydrogen ions? Well, a neutral solution is a solution that has the same pH as water. And the pH of pure water at 25 degrees is 7. Because the concentration of hydrogen ions of water is 10 to the minus 7. A minus log of 10 to the minus 7 is 7. What happens with acidic solutions? They are the ones that have more hydrogen ions than water has. So numbers that are larger than, concentration of hydrogen ions that are larger than 10 to the minus 7. And if you remember, we talked about 10 to the minus 6, 10 to the minus 4, 10 to the minus 3. If you do the pH, the minus log of those numbers, you end up with 6, 5, 4. So a pH of an acidic solution would be a number which is smaller than 7. 1, 2, 3, 4, 5, 6. And also, it doesn't have to be integers. 6.5, 3.2. Those are acidic pHs. And what would be the pH of a basic solution? Well, basic solutions are the ones that have fewer hydrogen ions than water has. So for example, here, I gave the example of 10 to the minus 8. So if you do the minus log of 10 to the minus 8, that is 8. So a solution that has a pH higher than 7 will be a basic solution. So suddenly, instead of working with slightly cumbersome numbers, which are negative powers of 10, you're using positive numbers, 1, 2, 3, 2.7, 13.8. And it's easier to see if they are above 7 or below 7. The 7, the concept of acidic, basic, and neutral solution holds at any temperature, because at any temperature, whichever it is, you will have for water, you will have the same amount of hydrogen ions as hydroxyl ions. But the number 7 only holds at what we call room temperature, because the number of hydroxyl ions and hydrogen ions at other temperatures for water will be different. So the concept of having the same number of hydrogen ions, or having more or having less, works at any temperature. The fact that pH of neutral solution is 7, a pH of an acidic solution is smaller than 7, a pH of a basic solution is more than 7, not only holds at room temperature. You can play with the equation. You can, as the same as you define a pH scale, you can also define the pOH scale, which is one, it's less used, and there are pH meters, not pOH meters, but it is only used with bases, and bases deliver as hydroxyl ions, but it would be minus log of the concentration of hydroxyl ions. You can play with between pH minus log of concentration of hydrogen ions, or the concentration of hydrogen ions, which is the inverse of the log, 10 to the minus pH. And you can play with the concept that because the concentration of hydrogen ions times the concentration of hydroxyl ions for water is 10 to the minus 14, that means that the pH plus the pOH equals 14. And if you're not convinced about the maths about that, just ask me and we can do it quickly in a session or in a tutorial. In this slide, I'm giving you a few exercises for you to practice using the questions in the previous slide. Then in them, I either give you the concentration of hydrogen ions, or I give you the pH and I ask you the concentration of hydrogen ions, or I'm telling you that what you are working with, the hydrochloric acid or the potassium hydroxide, they are a strong acid or a strong base. What do I mean with that? If you remember from a previous slide, it means that all the hydrochloric acid, all the potassium hydroxide, KOH, will have reacted to give me ions. So as many moles of hydrochloric acid I have to start with, I will generate those moles of hydrogen ions. As many moles of potassium hydroxide I start with, I will generate that many moles of hydroxyl ions in the reaction. So I'm going to ask you to stop the video and have a go at the exercises. Stop the video now, please. This is the answer to the exercises. I'm not going to do them live, not to make this video too long, but do ask me if you have any questions about how to calculate these pHs. Just quickly, whether the solution is an acid, basic or neutral. Well, any pH above 7 will be a basic solution. So for example, this would be an Israeli basic solution. The 1.69, which is the pH of this hydrochloric acid of that concentration, that's definitely an acidic solution. The solution of potassium hydroxide, 12.6, the pH is 12.6, that's a basic solution. And finally, a solution that has a pH 3, again, is an acidic solution. In the previous examples, I always either gave you the concentration of hydrogen ions and asked you to calculate the pH, or I told you that the compound was a strong acid or a strong base. And that was to help you, to allow you to calculate the pH. Because when you're working with a strong acid or a strong base, all the acid, or the base, in this case the acid, will be dissociated. So all these moles of strong acid will make the same number of moles of hydrogen ions. When you have a weak acid, that is not the case, because when you have a weak acid, only a small proportion of the acid will be dissociated. So only a proportion of the moles you started with of acetic acid will go to make hydrogen ions. So for any calculation of pH for a weak acid, we need to know the acidity constant of the acid we are looking at. So we need to know two things. One, how much acid we've got to start with, and how is it going to dissociate? What's the acidity constant of that acid? And with that, we can do the problem. So because it's beyond the scope of these videos to talk you through these exercises, I'm going to leave it at that. If you are curious about how to solve this problem, just drop me an email and we can organize a tutorial, or we can discuss this exercise in class.